All right, this is a solutions video for this worksheet that I've called A Plus Physics. That is a web page that is called A Plus Physics. They have all kinds of great worksheets and examples, and it's kind of like a Khan Academy for physics. So they have a section on the unit that we're in, and these are some of the questions that were applicable. Number 1, a satellite of mass m sub s orbits a planet of mass mp at an altitude equal to twice the radius of the planet. An altitude equal to twice the radius of the planet. What is the satellite's speed, assuming a perfectly circular orbit? They didn't say angular speed. They said speed, so we're looking for a linear speed. So here's the planet. Actually, let me draw that a little bit bigger. Here's the planet. It has a radius r, but the satellite is located at an altitude. Altitude is the height above the planet, and that is a value of 2r. So what is the radius of this orbit, which I did not draw very well? The radius of the orbit, therefore, is 3r, and that is also the distance away from the center of that planet to the center of that satellite, and they want the speed, b equals question mark. If you draw a free body diagram on that satellite, the only force acting on it, the only force keeping it in that orbit, the only force that is creating the centripetal acceleration is the force of gravity between the planet and the satellite. There is a gravitational field that the satellite is under that has been created because of the mass of that planet. So let me erase all those field lines so they're not around us. So I'm going to sum the forces inward on the planet. It's the force of gravity acting on the planet, which is equal to the mass, the force of gravity acting on the satellite, which is equal to the mass of the satellite, because I'm summing the forces on the satellite. This dot represents the satellite. There we go. Times the centripetal acceleration. We want the linear velocity, so we're going to use the definition of centripetal acceleration that's most useful, which is v squared over r. And that equation r is the distance between the center of masses. So big G, mass of this planet times mass of the satellite divided by the distance of the center of mass is squared. In this case, they called that distance 3r, and we're going to square it, equals the mass of the satellite times velocity squared divided by the radius of the circle that it's going around, which happens to be 3r, and then we solve for v. So mass of the satellite cancels. I'm going to multiply both sides by 3r, and one of those squares goes away, and I will take the square root and get the velocity of that satellite is equal to big G times the mass of the planet divided by 3r. And there is the answer. All right, the next question should be straightforward, but it's a great question because it's making sure you understand what the definition of gravitational field intensity is. Force of gravity, gravitational force. That is not what they asked for. They asked for the gravitational field intensity. That is little g is equal to what? Big G times the mass of whatever is causing the gravitational field divided by r squared. This is gravitational field intensity. It's inside the big G equation. I'll say mass of the planet, mass of the object over r squared. There is the gravitational field that is creating that force of gravity on object m naught. So what do they want to know? They want to know which of the following changes would increase that gravitational field. So increasing the mass of the object, that is a no. Notice that I'll put this little planet over here, that mass of the object is not in the equation for mass, or for the gravitational field. It's the mass of the planet. Increase the mass of the planet. Here it is. Yes, that works. That one works. Decrease the spin rate. That has to decrease in omega. You could say decrease velocity. It decreases the, actually it increases t because they're inversely related. T is the period it takes. T is the period. By decreasing the spin rate, you increase the period that it requires to make one cycle. Decrease the separation distance between the object and the planet. That's that value. And if I decrease it, that means the denominator gets smaller, and that would increase the gravitational field strength. So that question is intended for you to ensure you understand the definition of gravitational field intensity, as well as how it is related to the mass of the planet causing the gravitational field, as well as the distance away from that center of mass. This next problem, I'm going to point out there's a typo, and I keep forgetting to tell you guys that, and I'll explain in a minute. But this problem is using this linearization of data skill I've taught you before. So a space probe is sent on a mission to map out the gravitational field intensity. So what's the equation for that? That is G equals big G, universal gravitational constant, 6.67 times 10 to the negative 11, times the mass of whatever the object or planet that's causing that gravitational field, divided by the distance away from the center of mass is squared. In the vicinity, okay, back up. A space probe is sent on a mission to map out the gravitational field intensity of the vicinity of a satellite of planet X. So I've got some planet X. Here's my planet X. And that planet is creating gravitational field lines. And we're going to have a probe that actually goes out and measures those gravitational field values as you get closer or farther away from planet X. So let's go look at the table of data. We have the distance to the satellite times 10 to the 6 meters. So that's 2 times 10 to the 6th meters. I believe that's 6 zeros, right? So 1, 2, 3, 4, 5, 6. That's 2 million meters. 2.5 times 10 to the 6 meters, 3 times 10 to the 6 meters, and so forth. And at that location, 2 times 10 to the 6 meters, the gravitational field intensity is 13.3 newtons over kilograms. Newtons over kilograms is the same as meters per second squared. Let's look at why. Newtons over kilogram. What's a newton? That is a kilogram meter per second squared, and then I divide by a kilogram, and my kilograms cancel. That is a meter per second squared. So that's what you would expect your field intensity magnitudes to be in units. 9.81 meters per second squared is what you're exposed to when you're on Earth. So there's all our values. And that's what the probe gave us. Someone sent the probe out there. Elon Musk had his SpaceX team send the probe out there, and it got that data in that table. So A, on the axis below, plot the gravitational field intensity versus the distance r to the satellite. Remember, whatever came first becomes the y value versus whatever came second is the x-axis. So again, it's little g versus r. And sure enough, they went ahead and added that for you, so that made your life easier. Now I'm going to ask you the question before you start plotting that. Look at the value g equals m of the planet over r squared. Move r squared over. G times r squared equals big G times mass of this planet. Now, remember what a straight line looks like? We have y over x equals some constant, which we call slope. This value on this side is definitely a constant. That's big G times the mass of the planet. The mass of the planet's not changing. And then we have on the left-hand side of the equation, g times r squared. And that is our two variables. And hopefully you see that g is not directly proportional to r. It's directly proportional to 1 over r squared. So we're going to plot these out, and we should not get a straight line. So distance to the satellite, so I have 13.3. I'm going to do this quickly, so bear with me. 13.3, we'll say is right about there. And that is 2. Whoops, that's on 1. I should have done this before I made this video. The second data point is 8.4. I'll call that right approximately there. And 8.4 has a value of 2.5, so I'm right about there. This isn't going to be perfect, because I'm hurried. 5.9, so somewhere in the middle. And 5.9 gives me a value of 3, so where's 5.9? Something like that. And then I have 4.5. 4.5. And that number should be at 3.5, so somewhere right there. And then I have 3.3 for field intensity at a 4, so somewhere right about there, we'll say. And then I have field intensity of 1.5, somewhere right about, that's 1, so even lower, and that's 6, so somewhere like right here. Sure enough, not linear. Draw an appropriate best fit line or curve. So here's the curve. There we go. So I have just completed A and I've completed B. C, using that best fit line, what distance, that would be R, corresponds to a field intensity of 2.1 newtons per kilogram? So where's 2.1? Well, this is approximately 3. Here's approximately 2.1. And then I come over here and I look right about there, and I come down here and I find my number to be approximately, did I do that right? I don't know, I got around 4 point, it's not 4.5, I'll call it 4.25 times 10 to the 6 meters. Obviously, based on how you drew that, you might get something slightly different. It's not perfect unless you plugged it into your calculator and had it curved fit. Okay, now I wouldn't have given you this question. I would have asked you how to plot. What do I plot in order to create a straight line so that I can determine the mass of the planet? Well, how do I determine that? I'm trying to create that y over x equals m. Little g times r squared is the same as g divided by 1 over r squared. So I would put g divided by 1 over r squared is equal to big G over mass of the planet. This would be on my y-axis. This 1 over r squared is on my x-axis. And that's actually what they have you draw. So I have to calculate 1 over r squared. So 2 times 10 to the minus 6. What is that? And I've already done that. And I'm going to fill in my table real quick. I get 2.5 times 10 to the minus 13. And then I have 1.6 times 10 to the minus 13. And then I have 1.1 times 10 to the minus 13. Then I have 8.16. 8.16 times 10 to the minus 14. You might put that as 81 well, I'm not sure. I got to think about that. 6.25 times 10 to the minus 14. 2.78 times 10 to the minus 14. If I want it to be minus 13, it's got to be 0.816. In fact, let's change that so that they're all to the 13ths. Let me see something here. What did I do? What did they have us plotted as? Oh, to the, okay, they have the 14 and the 13 in here. Good. Let me leave it back. Go back. Okay. So minus 14. Okay. Now I can plot those data points. I'm not, for the sake of this video, I think you understand what we're trying to do. I'm just going to eyeball it based on my results. And I'll give you what we do next. Obviously, this is not perfect. And then some data point up here. And then there's a best fit line. And then I'm going to use 2 points. Okay, so it's approximately, looks something like that. Guess what? It's linear. Use the plot and best fit to determine, and this is a typo. This should be mass of the planet, not satellite. And it's not my typo, just so you know. What does this slope equal? Well, we know that G over 1 over R squared equals big G times mass of the planet. This is a constant, and that is the slope. So if I find the slope, it will equal big G mass of the planet. Now, you're not going to use the data points. In my original graph, I had that point, and my other point was somewhere in this region. And so my line doesn't look exactly like, I gotta go. Oops, I don't want to do that. Go back. I want to get rid of that dot. Perfect. So I used something in that region. So I found the slope. And then don't forget, it's y2 minus y1 over x2 minus x1. Not the easiest thing to do. So here's my x2, y2 point, and here would be my x1, y1 point. And then I would actually find those values. I found the delta y to be 4.66 times 10 to the minus 13. No one, oh, not minus 13. Everyone's numbers are going to come out to be slightly different. 6.67 times 10 to the minus 11 was my delta x. So my slope was 6.99 times 10 to the 23. And that was in units of, slope is newtons over kilogram divided by meters. Meter per second squared. Oh, never mind. That's actually not my slope. Sorry. Sorry. My slope ended up being 4.666 times 10 to the 23rd. That was my slope. And the slope is in units of newtons over kilograms over meters per meter squared. Meters to the negative 2. What is my units going to come out to be if I want math? It will come out to be, come on, Deb, kilograms. Slope is equal to G times mass of the planet. Mass of the planet equals slope divided by big G. So I take 4.66 times 10 to the 13 divided by 6.67 times 10 to the minus 11. That's on your green sheet. And I found my mass of the planet to be 6.99 times 10 to the 23, and it'll come out to be kilograms. Hope that helps.